So this is Unit 2, Day 2. We're finally going to get a look at interference. I'm going to do a couple of notes here in our booklet, this page and then one after it. But before we dive into those notes, which actually won't take very long, I want to go and just show you a couple of things. I'm going to call this particular little presentation, I just want to offer you the what goes without saying presentation. You don't have to copy anything here, but I just want to show you some things that I think as teachers, we often assume students are thinking because it's in our minds and we're expecting you to read our minds, and that's just not fair. So here's some subtle little stuff that's actually really important, and it probably shouldn't go without saying. We should probably overtly say it. So how does this whole two-slit interference pattern come about? Well, we know if a couple of people grab a bed sheet and start shaking the thing, so maybe they're shaking it like crazy. One person's grabbing it here and shaking it up and down. Another person's grabbing it here and shaking it up and down. When those waves travel across the sheet, they're going to start to interfere. And there might be some places where when you look at the pattern of waves, it's really, really impressive, like along there or there, those kind of bands. But there might be some other places where there's actually very, very little shaking because it's destructive interference. And that happens whenever you have waves from two sources arrive at one spot in a material, and they may be in or out of phase. They may be cooperating or trying to totally fight with each other, right? So that's just general interference. Let's go and take a look at how this might happen now for our story with light coming through a couple of narrow little openings. If that light can spread out and then land on the wall on the other side of the classroom, if it arrives in a way like this, where right as one wave is trying to push this way and the other one's trying to pull, those are going to be fighting all the time, and you're going to get destructive interference. Things are going to be very dark or very quiet if it happens to be a sound experiment. But if both waves arrive in phase, as we would say, where they're both working together, then it's going to be a very bright spot on the wall, a big bright dot, or a big loud spot if you were listening to some sort of sound experiment. And so it's just an issue of whether or not these waves from two different sources arrive in phase or whether they arrive out of phase. Now, the good news is you can easily get the light to spread all over the far wall of a classroom just by sending your laser beam through a narrow little opening. It kind of comes back to that Huygens radiator thing, and there's just like one choir member that can sneak through the door, and when they sing, the sound just fans out all across the room. So if you had some back wall in your classroom over here, then all along that wall, you could potentially have light strike it if you force it to go through a very narrow opening, right? It just does that spreading out, which we call diffraction. Okay, so that's what happens when it goes through one narrow opening, and this might be many, many meters across the wall, like 2-3 meters across the wall if you get the spreading just right. Well, the plan is, what if we were to put two slits really close together? Like I'm talking really close together, less than a millimeter, right? Maybe 1/10 of a millimeter apart. Then each of those openings is going to create a fan of light on the back wall. So here's one fanning along the back wall, and here's another one fanning along the back wall. And there's definitely spots where both of these fans of light can reach. And those are places where the two waves can start to interfere. And you could get bright spots or you could get dark spots. So everything we're going to be looking at is really coming back to this idea that waves from these two sources, these two openings, could actually strike the observer, and they might be in phase or they might be out of phase. And that observer could easily be standing way off to the side. They might not be in the center line of the experiment, right? The center line might be here. They could be off to the side, but these fans of waves will actually spread out by quite a bit, and they'll easily cover the full back wall of the classroom. Okay, so let's look at the next issue here. Those waves are now going to create these spots on the back wall where they arrive constructively or destructively, creating perhaps loud or quiet regions along the back wall if it's a sound experiment, or maybe bright or dark spots on the wall if it's a light experiment. And so what we can see is that these waves are fanning out, right, from both sources. That way they can both hit the wall on the back side of the room. Okay, next issue. This is one thing where I think as teachers we really do drop the ball, and we don't overtly talk about how badly we draw these pictures in terms of being to scale. We never draw them to scale because there are so many different sizes of things that are happening in this story. So I've got my laser beam on the left, and it's actually hitting two openings here. They're just so close together you can't notice that. And there are two beams of light that are making their way across the room. They're pretty much on top of each other and just at a slight angle. And then they go to the far back wall of the room and create some dot pattern over on the back wall. So I'm going to zoom in on this section over here for just a second. And here's what you'd notice. These two little openings. And they might be much, much less than a millimeter apart. And the actual opening sizes, well, they could be 10 times smaller than that even. So you could have openings that are maybe 1/100th of a millimeter that are then arranged 1/10 of a millimeter apart. We're talking about some pretty tiny dimensions for those holes, for how wide they are and how far apart they are. And then you go all the way across the classroom. So this distance as you walk it could be like 5 meters as you go across the classroom. And then you'll notice all these little dots on the wall. And if you were to measure from center and say, okay, well, how far is it to that particular dot? That might be just a few centimeters, right? So we've got things that are all different sizes. This is what we're going to call L, the length of your classroom. We're going to call this X, how far stuff is to the side over on the wall. And you go from meters to centimeters to openings that are much, much, much less than a millimeter across and maybe 1/10 of a millimeter apart from each other. And so it's horribly like diverse in terms of like differences of size from small to big. And we're going to go and draw it like this. And so this is really not fair, right? Because if you were to go and start taking a tape measure to this, that might be 1/100th of a millimeter. This might be 1/10 of a millimeter. And this might be 5 meters. And this might be, I don't know, 3 centimeters as you look at the pattern on the wall. So you've got things that are smaller than millimeters, around the size of centimeters, and then bigger than meters. It's just a really hard picture to draw nicely to scale. So instead we're like, yeah, okay, don't even bother worrying about getting it to scale. But just be aware of the fact that we're dealing with things that are totally different in size as we look at the whole picture. Now, there's one more thing we got to talk about. In PhysicsAP, we're only supposed to talk about half the story. But when you look at these patterns, you will instantly see both that and the other half of the story. So we might as well talk about it, but we just won't tell the College Board that we're talking about it. So here's the issue. When waves go to a small opening like this, like light waves, sure, they fan out, fantastic. But there are actually a couple of dark patches often where no wave energy gets to, kind of either side of center. And so each one of those two openings has trouble hitting one part of the back wall. And that ends up creating these dark patches of, I'm just going to call them dark patches of nothingness in your nice little pattern of dots over on the back wall. So then the dots come back, right? And then they disappear again for a second, right? And then they seem to come back. But we're definitely going to see some little sections of darkness where the pattern seems to disappear and then it comes back. And we will talk about that in the lesson after this one, even though it's not part of the course. Okay, here we go. Let's get down to business, right? That was a long preamble. So this is the 2-slit or 3-slit or 4-slit or 6-slit pattern. It doesn't matter, as long as it's 2 or more, you're going to get the exact same pattern on the wall. And sometimes we just use this thing called a grating that just has hundreds of slits and the laser is wide enough to hit about 6. So some important dimensions. We're going to need to measure how far it is from the middle of one opening to the middle of the next. And I'm going to call that D. That spacing, that distance from opening to opening, could be 1/10 of a millimeter. Another issue that will be important in the next lesson is how wide is each one of those openings. I'm going to call that A for aperture. That could be 1/100th of a millimeter. Right, so we're talking about some pretty small things. Okay, so this D in general, let's just say that D is very small, right? Maybe something in the order of micrometers. Maybe something in the order of even getting around the size of millimeters, somewhere in there. We're talking about some pretty small numbers. Now the wavelength of light that we send from our laser beam towards this mask is going to be very small, even smaller again. You might see blue waves in your story. And just so you know, for blue, the wavelength is, roughly speaking, Just going to try to get it to about 1 sig fig correctly. Oops, not 400 meters, 400 nanometers. And red, roughly speaking, is double that, around 800 nanometers. So these wavelengths of energy are very, very, very tiny. Now, the little graphic that I've stolen just off the internet here says, oh, you could use this with a white light source that sends out a beam of white light. Well, white light has a whole bunch of colors in it, right? It's got the full set of colors from the rainbow in it. The other option works a little better is to use a laser. So maybe we'll change the notes to say, hey, you could use a laser or you could use a white light source. The advantage of the laser is that if it was red, you would just get like a red dot here and here, and one there, and here and here. If it was a green laser, the dots are in a slightly different spot. And if you use a white laser, you kind of get these little rainbows. And the rainbows can be a little confusing to measure, and the dots are a bit easier to measure. But I guess you could use a white light source to get this to work. So the white light source, what's interesting about that is that it would have built into it many colors. We'll typically use the laser. Okay, so getting the scale right. These little openings that you see from there, they're actually here. These openings could be, in terms of distance from one to another, maybe 1/10 of a millimeter from one to the next. And this distance is your walk across the classroom. This could be a few meters. Okay, we're going to call that L. All right, so I'm going to say usually a few meters. Then when you look on the back wall, you'll notice that there are these dots. And we can go and measure the angles over to these dots, measured from the center line. Right? The physics equation we're going to look at says, hey, let me help you find the angle to that dot. That's the first dot from center, so we might call that angle 1. And it's the same kind of picture, just reflected on the other side, just to make it so my notes aren't all too cluttered up. Let's go from the center line over to that dot, the second one over. This angle all the way over to there would be angle to dot number 2. We actually name the dots. They get named with just little number names. So right down the center is called n equals 0. And this area here is going to be dot number 1, n equals 1. This would be n equals 2. And the same thing on the other side. It's totally symmetric. When you are over on the wall, sometimes you might want to grab a small ruler and measure how far is it from that center dot over to where the first dot is. And when we talk about measuring on the far wall of the classroom, I'm going to use the letter X to talk about that. This could be X1, the distance over to dot number 1. Or if you were to keep going, let me do it on this side. It's just a little less cluttered. If I was to do it over here, that could be X2. Right, the distance over to feature number 2. And by that, let me just draw that in right here so you can see what I'm talking about. The pattern on the wall could look like this. And right down the center, that would be n equals 0. And then on either side, this would be n equals 1. There'd be the one on the other side as well. This one would be n equals 2. This one would be n equals 3. And one of the things you can see is this issue that's not really part of the course, but n equals 3, 4, 5, n equals 6 seems to have vanished, but then 7 is back. And we're going to talk about why 6 has vanished in the next lesson. Okay, it's not really part of the course, but we are going to talk about it. Now, if you were to take like a fancy little light detector, some little wand that at the end of it can actually sense light, if you were to take that wand and then bring it by, let me rotate this a little bit, maybe just the end can detect light. And if you were to wiggle it by here and just walk along the room, and maybe it's recording a graph of how intense the light is here, the end of the one is saying, oh, it's so bright there. So we'd be sitting there going, beep, 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 beep. Right? And then here it would say dim, and then bright, and then dim, and then bright, and then dim, and then bright, and then dim, and then bright. If you made a record of that as a graph, that's what this graph is down here, which you'll see in a lot of textbooks. So it's actually just trying to show you how bright that dot is. That's the peak of this graph. And then the next dot is right here. So in terms of reading this graph, this is n equals 0. This is n equals 1, right? And it's just recording the intensity of how bright those dots are. You will hear me jokingly call this the confusing graph of brightness, because the first time you look at it, you're going, what is that? And it's just a graph spatially of how bright these dots are as you go across. Okay, let's finish this page off with two equations. Actually, it's going to be kind of one equation which we'll use twice, and I'm going to stick them in some boxes here. Then on the next page, we'll explain why it's true. So there is a beautiful physics equation that will tell you what angle you would have to be twisted at in order to find those bright dots. And here it is. So this is the story for angles to the bright dots. The equation, which we'll see why it's true on the next page, it's d times the sine of the angle. Now right away you got to ask, well, which angle are you talking about? Are you talking about like the angle to dot 1 or the angle to dot 2 or the angle to dot 3 or the angle to whichever angle you want? So there are a whole bunch of angles in this story, so maybe I'll put a little subscript down there. It could be angle 1, angle 2, angle 3. You can find that angle because it abides by this equation. It's equal to a big integer here, which is the dot number, multiplied by the wavelength. So you can put in whatever integer you want in order to find those bright dots. So you will find yourself putting in like the number 1 or 2 or 3 or 4 in here for n. I guess you could put 0 in too, and it'll just tell you that, yeah, 0 angle to the 0 dot right down the center. Now, sometimes people are going to ask you, well, could you locate this little dark spot in between the dots? And I would say, sure. We got dot 0, dot 1, dot 2. Well, that's in between dot 2 and dot 3. So if you want to start talking about angles to the spots in between, we'll just put in half numbers. It's really not a big jump in logic here, right? So angles in between the dots. No problem. Same equation, don't change that. D times the sine of the angle is equal to some number we're going to put in times the wavelength. But now this time don't put in whole numbers. If you want to find spots in between, oops, mistake there. If you want to find spots in between, then go ahead and put in like half numbers. So you could put in numbers like 1/2 or 1.5 or 2.5 and so on. Right? You can keep going with that idea. You could put that in there, and that would help you find those places in between the dots. That'll work fine for the homework, but it's perfectly reasonable for you to say, okay, but why is it true? Right? Why does that actually happen? And I'd like to show you that as our last page of notes for today. I'll show you the math behind it. And you don't have to reproduce this math. You're not like responsible to be able to redo it. But if you're wondering, well, why is it true? Let's see if we can figure out why. So on the right side here, this is the screen. This is the back wall of the classroom, many meters away. And here's my two slits right here. Two little narrow openings that are probably 1/100th of a millimeter across and maybe 1/10 of a millimeter apart, center to center. So people would say, oh, well, let's talk about that, right? That D distance, right? From opening to opening, right? From there to there. Sure. Okay. You then go many meters across your classroom. Let me just draw the center line in really faintly here. So there's the center line. You go many meters across the classroom and you find this pattern on the wall. There's a bright dot right here. And then maybe there is another one. And maybe here is another one. Same pattern down here. Like that. And they're all named, right? This is n equals 0. And this one on either side would be n equals 1, n equals 2, and so on. And there could be a dozen of them on either side. All right. So let's draw what's going on with dot number 1. Why is dot number 1 so bright? Why did it work so well there? So I'm just going to draw the paths of light, the paths of the rays, as they go from that opening to that dot and the other one. Okay, so two paths that both lead to this special spot on the wall that's in just the right spot for it to actually be very bright. Now remember, this picture is horribly not to scale. These two openings down here on the left are about 1/10 of a millimeter apart, but it's several meters across the room. And the distance from red dot to red dot is maybe a couple of centimeters. So this thing's definitely not to scale. It's terrible, right? It should look more like that. When you actually look at it slightly better in terms of being to scale, you can see that these two rays are pretty much parallel. They're pretty much at exactly the same angle compared to the center line, right? So if there was a center line in here, there's this tiny little angle in there. All right, well, let's go back and look at this. Maybe we should leave a little note in here. These two rays, they're, let's just say, basically parallel. They might as well be. But in this drawing, they totally don't look like they're parallel. That's just because it's not to scale. Okay, so there's an angle going on here that talks about, well, what kind of angle is it up to dot number 1? So this would actually be theta 1. So what's so special about theta 1 that's making this work? Well, that bottom ray, that bottom distance is a little bit longer than the top one, but not by much, okay, just by a tiny bit. In fact, if you were to go and measure, right, they're together here, together here, together, 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 and just kind of back this up. Somewhere right about here, you can see that this bottom ray is about that much longer, that bottom path. That little yellow space in there is everything. That tiny little yellow distance is what this entire chapter is going to be about. Like, how much space is there in there? Is that enough space for the waves from the lower dot to actually get a full extra wiggle in, or maybe 2 extra wiggles, or 3 or 7 extra wiggles? Because if it's a nice complete number of extra wiggles, then things will agree over on the screen and you're going to get bright dots. So all of these bright dot locations are places where this path length is just beautifully perfect. Let's actually zoom in and let's draw these little 2 Huygens radiators again, like right up here, just where we have a little more room. Okay, just a zoomed in version of what's on the left. And you've got these 2 rays that are leaving you parallel like this. And what we're trying to focus on is that tiny extra little bit of length that we've got right in there. That's it. After that, the 2 rays are side by side. Okay, some dimensions on here. The distance from the middle of one opening to the middle of the next, that's what we call D. It's probably maybe 1/10 of a millimeter. Okay, so that's D. And I can see this path length is actually, this extra path length in yellow is actually less than D. It's super tiny. But if I add in maybe just a little right angle triangle in here, like that. There's a neat little thing with similar triangles that happens where this angle, theta, ends up being the same as the angle up here in that right angle triangle. And so if you're trying to figure out how long this yellow extra path length is, and you know the distance from dot to dot, that's like a hypotenuse in a right angle triangle, and you could use sine to get there. So that extra path length, if you play around with the SOHCAHTOA, sine of theta would be the extra length divided by d. So if you multiply by d, that extra path length is actually equal to d times the sine of theta. That's how much longer one path is than the other. And now you can see where this equation comes from, right? That change in the path length, the extra little bit of path you've got from the lower path to the top path, that's equal to d sine theta. And what we're wondering is, hey, does that happen to equal an interesting number of wavelengths? Like, is it off by 1 or 2 or 1.5? If it's off by 1, that's this bright dot number 1. If it's off by exactly 2, that's bright dot number 2. Those would be in phase bright spots. But if this question mark is a 1.5, well, then they fight each other and it's actually very dark there. So it's actually a pretty simple idea, just with a complicated picture, where that d sine theta actually calculates how much longer one path is than the other. Okay, over on the far wall of the classroom, it would be really common to go and grab a small ruler and measure this distance, which we're just going to call x. So that would be x1. Now I could draw another x going from the center up to number 2, but maybe I'll draw it down here a little bit easier. So this could be x2. If you want to get some math rolling here for how big are those x's, no problem. We can just do a little bit of grade 10 right angle trigonometry. That would look like this. This is not going to be to scale, but on one side of the room you've got that little multiple slit opening. Okay, actually, let's just draw it with 2 openings maybe. That was bad. Let me draw that again. Got my 2 openings. Okay, light's going to go through there. There's a center line, and then you go across the classroom, and then here's the wall, right, where that light's going to hit the wall. The distance across the classroom is going to be L, could be a few meters, and then maybe you've got your first dot out here following that path. Well, if we're going to call the distance along the wall x until you get to some feature like a dot, then there's just some nice simple grade 10 math that says, oh yeah, well, tan of that angle would be the distance across the wall, which is usually around a few centimeters, divided by the length across the room, usually a couple meters. Now, if you want the trig to work, you have to make sure you're working totally in meters or totally in centimeters, but you would see a total difference in size between those two things. The x is much tinier than the L typically. Here's a neat little approximation you can do. If you don't believe me that this is true, try it with your calculator. Try taking the sine and the tangent of some really small angles, like 2 degrees. And what you'll find is that for small angles, and by that I mean, less than 10 degrees, which is typically what we'll have. For small angles, the tangent of an angle is actually pretty close to the same size as the sine of an angle. It's just the way the right angle trigonometry works. So you could do this. You could say, well, hang on. I've got this grade 10 trigonometry here that says x divided by L is equal to tan of theta. But then on the first page, we said that d sine theta is equal to n lambda. Well, if I divide by d, sine theta would be n lambda all on top of d. Okay, so I could say you are pretty close to the same size as the sine of theta, which is n, the dot number, lambda, the wavelength of light, divided by d, the distance from one opening to the next. And so you can patch those together and you can say, oh, okay, looks like x on top of L is going to be pretty close to n lambda all over d. That actually suggests that the dots will be pretty much evenly spaced when you look at them. And as long as the angles are less than about 10 degrees, that's actually true. So that can be used as a quick way to find any one thing that's missing out of those 5 variables that are there. And that's it. That's as far as we're going to go today. We're looking at that 2-slit pattern. One of the things that we're not talking about, not yet, is the fact that there are these little dark patches where the pattern seems to go away for a little bit. We will come back to that, okay, in the next lesson. Talk about why those patches are there, or talk about how you can actually locate where those patches are. But for the 2-slit pattern, that's the set of formulas that we're going to use. That's if it's 2 slits, 3 slits, 4, as long as it's more than 1 slit, that's going to be the math that we're going to use.